Hello and welcome back, my fellow path integrator. Today we're going to do something absolutely incredible. We're going to use Feynman's integration technique to prove this formula, to prove that this double integral is equal to -2 times the zeta function of 3. And how are we going to do that? Well, we start with a trick that we have already seen in one of my previous videos. Maybe you remember it. If you have seen it, it's the one where I solved the Basel problem according to the proof of Tom Apostol. And he starts with an integral that looks like this. So it's basically like the integrand above here, but without the logarithm in the integrand. And he shows that this integrand is equal to the zeta function of 2. So this thing here is equal to zeta of 2. How does he show that? Well, he sees that this integrand here, 1 over 1 minus xy, looks a bit like a geometric series. So we can write this as the sum from n equals 0 to up to infinity of xy to the power of n. And then we have dx dy, and then we can just pull the sum out of the integral because the sum is converging, at least if the x and y are smaller than 1. So actually this is an improper integral and we have to deal with limits, but this works if we just treat it like this. So doesn't matter if we treat it with limits or not, it yields the same result. So we have like the sum from n equals 0 up to infinity outside of the two integrals, and then we have xy to the power of n dx dy, and then we just have to integrate with respect to x and with respect to y, which is kind of simple because it's just a polynomial, and we evaluate it at the limits 1 and 0, and eventually what we will get then is 1 over n plus 1 squared. And if we just perform a shift of the index, so if we say that the index starts at 1 and goes up to infinity, then we have 1 over n squared, and this is the zeta function of 2. So how are we going to use that now to prove the formula above here? So how are we going to introduce the logarithm into the integral? Well, here is where the Feynman trick comes into play. So we have this function, and we have this integral here from 0 to 1 divided by 1 minus xy dx dy is equal to the sum starting at n equals 1 going up to infinity divided by 1 over n squared. And we introduce the Feynman parameter in the following way. So we say that our function I of a should be the Feynman parameter, is still the integral, and here we have x to the power of a, y to the power of a divided by 1 minus xy dx dy. So as you can see, if we set a to 0, then we have x to the power of 0 times y to the power of 0, and this is just 1, so we get the exact same integral. So by setting a to 0, we get our original integral back. Now what we do, we have to understand how is the relation to the zeta function now. So let's just calculate it with the geometric series again. So we have 0 to 1, and then we have the geometric series from n equals 0 up to infinity, xy to the power of n, and then times xy to the power of a, dx dy. So this in the end is just the double integral from 0 to 1 times the sum, and then we have xy to the power of n plus a dx dy. So this in the end means that we have the sum from n equals infinity up to from n equals 0 up to infinity times the double integral from 0 to 1 xy to the power of n plus a. So this is quite easy. This is once again just a polynomial. So what we would get here is the sum from n equals 1. So let's just do the index shift already, because here we would get a plus 1 with the integration, but we just omit that plus 1 by doing the index shift just now, and what we will get now is 1 divided by n plus a squared. So what we now know is, so let's just copy that down, no, let's just rewrite it. So we have the integral, the I function, which is dependent on a, is the double integral from 0 to 1 of xa ya divided by 1 minus xy dx dy, and the whole thing is equal to the infinite sum from n equals 1 up to infinity, 1 divided by n plus a squared. And now we do the derivative. We just take the derivative now. So what we do is we take the derivative with respect to a of the function I of a, and of course of the right side as well. So the derivative of this integral, of this double integral, with respect to a will give us a logarithm. So let's write it here. So when we just pull the differential into the integral here, and then we take the integral with respect to a, then we will get a x to the power of a, y to the power of a times log of xy, and the thing cancels here. So this is what we will get if we take the derivative of the whole integral, and the whole thing is equal to the derivative with respect to a of that infinite sum up to infinity n plus a squared. So all we have to do now is take the derivative of this thing here. So let's put it down here. So the derivative of the sum with respect to a is just minus 2 times the sum, the infinite sum, not starting at 0, sorry, starting at 1, going from n, going over n plus 1, not n plus 1, sorry, I'm getting ahead of myself, n plus a to the power of 3. So this means that the double integral from 0 to 1, xa, ya, log of xy divided by 1 minus xy dx dy is equal to minus 2 times the infinite sum over 1 divided by n plus a to the power of 3. And all we have to do now is set a equal 0, and then we get the result that we actually wanted, that the double integral over log xy divided by 1 minus xy dx dy is equal to minus 2 times the zeta function of 3. So this is our final result, and it's absolutely amazing how you could use Feynman's technique to prove that this integral actually is another representation of the zeta function of 3. Alright, I hope you liked it. Leave a like, subscribe to the channel, and let me know in the comments if you would like to see how one can prove that a little bit simpler with integrating by parts. Alright, see you in the next video. Bye!